Okay, today we're going to start looking at what is and isn't a function and inverse functions. So suppose we define the following function f as the ordered pairs listed. So -2 goes to +2, -1 goes to 1, 0 goes to 0, 1 goes to 3, and 2 goes to 5. We've defined this function f so that the second component, the y component, these y's, -2, 1, 0, 3, and 5, don't repeat. They're only used once. So since they're only used once, we can form another set of ordered pairs from f by changing the x and y values, and we'll call this set G. But the cool thing is that because none of those y's repeated, those y's now down here become my x's. And hopefully you remember from functions that the x cannot repeat. So I took my function f, I had x and y's, the y's were in red, and then I made a new function g, which is the inverse of f. These two are inverses because we switched their x and y values. And we can say that g is a function because none of those new x values, the red things, repeated. So because we can do this, this is called a one-to-one relationship. One-to-one relationship means that the y values don't repeat. And since the y values didn't repeat, the original f is 1, 2, 1. That means that another way to look at that is that I have f, and then g is the inverse. And since g is a function, then f was also 1-to-1. So in a one-to-one function, each x value, or the input, corresponds to only one y value, and each y value corresponds to only one x value, which is why it's called one-to-one. One x goes to one y, and then it's done. No one repeats at all. No x repeats to be a function, no y repeats to be one-to-one. So if you look at the example right here, figure 1, this is not one-to-one because of this. 2 went to 7. 7 should be done. No more friends for the 7y value. But the 3 also went to 7, and so this is not a one-to-one function. It is a function. None of these x's repeated. It's just not a one-to-one function. In figure 2, 1 goes to 5, 2 goes to 7, 3 goes to 6, 4 goes to 8. Since all the y's over here only have one x value each, none of them are repeated, it is a one-to-one function. So a one-to-one function, by definition, means that for the elements a and b that are in the domain, so here's my x's, I have my a and I have a b. Then here's my y, my range, f of a, f of b. A goes to f of a, b goes to f of b. A does not equal b because it's a function, and if a equaled b, the x's would repeat, I wouldn't be a function, which then also means that f of a does not equal f of b because the y values are all unique. The y values cannot repeat. So let's look at this in practice in a mathematical sense. So on the next page, it says determine whether each of the following is a one-to-one function. So we can do this a couple different ways. From an algebraic standpoint, let's use that definition from the previous page that said a does not equal b, then f of a does not equal f of b. So I'm going to find these two things. I'm going to find f of a, f of a is equal to negative 4a plus 12. And then f of b is equal to negative 4b plus 12. And we're going to set them equal. Negative 4a plus 12 equals negative 4b plus 12. If you move everything to one side, these 12s are going to cancel off. So you get negative 4a equals negative 4b. And then you end up getting that a equals b, because you can divide both sides by negative 4. So if a equals b, then f of a has to equal f of b. This means that it is one-to-one by definition. So since a equals b, f of a equals f of b, 1 to 1. At the bottom of the page, it says something about a horizontal line test, and I want to give you a graphical representation of this real quick. So if I were to graph example A, that's a linear function with a y-intercept of 12. So there's my y-intercept. Its slope is negative 4, so I go down 4/1. Not my best drawing, I apologize, but there's my graph. We use the vertical line test to tell if something's a function. We use the horizontal line test to tell if it's 1-to-1. So when I draw horizontal lines on this, each horizontal line is only allowed to touch my graph, the line, once. Every time I draw a horizontal line, it only touches once. That's another way to tell that it's 1 to 1. So let's do another example. So the next one is not 1-to-1, and I can tell you that off the bat by looking at that x squared term. So for example, if I do, let's say, f of 3, that's going to get square root of 25 minus 3 squared. 25 minus 3 squared is 25 minus 9, which is the square root of 16. The square root of 16 is 4. If I do f of negative 3, same idea, I get 25 minus negative 3 squared. But when you square a negative, you get a positive. So it's going to be 25 minus 16 minus 9, which is 16, which still gets me 4. So two different x values resulted in the same y value. The y's can't repeat if I'm 1-to-1, so this is not 1-to-1. The other way you can tell is they gave you a graph down here of what this looks like. You could have made the graph by graphing points, but I can use, again, the horizontal line test. And you see how when I draw these horizontal lines, I touch the graph more than once? Well, that makes it not 1 to 1. So now we can use this horizontal line test, or we can show algebraically that something is 1-to-1. So on the next page, they give you some graphs, and they already drew some lines. Let's draw our own. So if I draw a horizontal line here, I touch it 1, 2, 3 times. This is not 1-to-1. On this line, though, I can draw as many horizontal lines as I want, but I only touch it once, so this is 1-to-1. So tests to determine that functions are 1-to-1. If you can show that f of a equals f of b, that implies that a equals b, which means that it's 1-to-1. In a 1-to-1 function, every y value corresponds to no more than one x value, aka the y's cannot repeat. So if you find two x values that produce the same y value, that's what we did in 1b on the other page, sketch a graph and use the horizontal line test, which is what we did right above. And then you can tell whether it's a 1-to-1 function or not. So you know all these different ways, and they're all equivalent as far as being right or wrong to show if something is 1-to-1 or not. So now let's take a jump and find some inverses. So to tell if two things are inverses, we have to do composition of functions. We have to do two things. So if f is 1-to-1, that means the inverse of f, which we call f to the negative 1, is a function. And since f is 1 to 1, then f inverse is a function, then we can do composition of two functions and say that g is an inverse. This g is like my f negative 1. If and only if these two conditions are met. This condition really means f of g of x equals x. And, not or, and. You must do both. G of f of x equals x. So let's use this rule to see if g is the inverse of f. Again, there's two parts you have to do. So part 1, I first have to do f of g of x. So that means f of something. I wrote an f right here, so I'm going to write f's rule down, which is right here, something cubed minus 1. The thing you're plugging in right here is g. So g is the cubed root of x plus 1. And so if I plug that into those parentheses, then my other parentheses also have to be the cubed root of x plus 1. A cubed root and a cube undo each other. So this is equal to x plus 1 minus 1. Plus 1 and minus 1 undo each other. This is x. Woohoo! We're not done. That's just the first piece. You also have to do g of f of x. It has to work both ways. So g of something, I wrote g here, so I'm going to go write down g's rule, is the cubed root of something plus 1. The something I'm plugging in is f. So f said x cubed minus 1. So in here I put x cubed minus 1. I don't really need those parentheses. So what I really have is the cubed root of x cubed minus 1 plus 1. Minus 1 and plus 1 undo each other. So I'm left with the cubed root of x cubed. Cubed root and cubed undo each other, leaving me with x. Now we can say f of g of x equals x. G of f of x equals x. Inverses. One small little note is this thing right here. Please don't confuse this. When you raise a function to a negative 1 power, it is the inverse. It is not this. No, not that. So when something is an inverse, what's happening is the x's are becoming the y's, and the y's are becoming the x's. In other words, the domain of the original, the domain of f, the original, is the range of the inverse, and the range of the original is the domain of the inverse. So the domain here becomes my range, and then my range becomes my domain. They flip places. Finding the inverse of one-to-one function. So find the inverse of each function that is 1 to 1. So the first thing we need to do is figure out, is this original 1 to 1? Because if the original is not 1 to 1, then we cannot find an inverse that is a function. It has an inverse. The inverse is just not a function. So right here, 1, 0, 1. Oh, I already repeated 1 and 1. And then 2, 2. 2 repeats. So f is not 1 to 1. This little symbol means therefore. Therefore, f inverse is not a function. Let's look at the next one. So I got to check your y's first. So I get 1, 2, 3, 0. I didn't repeat anything. So if I want to find g inverse, all you do is switch the x's and the y's. So instead of being 3, 1, it's 1, 3. 0, 2 becomes 2, 0. 2, 3 becomes 3, 2. And then 4, 0 becomes 0, 4. The next one is a verbal description, gives me a table. And it says the number of hurricanes in North America during the span of time from 2019 to 2013. Sorry, 2009, not 2019. 2009 to 2013 is modeled by F below. And they give you the years and how many hurricanes happened. So the independent over here is X. Time is usually the X. Number of hurricanes is the Y. So if I look down this table, 3, 12, 7, 10, 2. None of my Y's repeat. So if I want to find the inverse, just flip the ordered pairs. Instead of 2009 going to 3, 3 goes to 2009. 12 goes to 2010. 7 goes to 2011. I'm going to run out of space, so I'm going to go to new line. Sorry. 10 goes to 2012. And 2 goes to 2013. There's my inverse. So on this page, we're going to actually find an inverse, not verify, but find the inverse. And so to do that, we do a couple steps. We switch to x and y. Step 1, interchange x and y. We're going to resolve for y, and we're not going to call it y when we're all done. We're going to rename it appropriately as f inverse or whatever the function was called. So f of x is a fancy way of saying y. So to do step 1, x equals 2y plus 5. There's step 1. I've switched x and y. Now I need to solve for y. So I'm going to minus the 5 over and then divide by 2. And I'm just going to write it so you guys can see it. That's really a 1/2 x minus 5 halves. And we're not going to call it y. We're going to call it f inverse of x. Let's try another one. So this is y. So we're going to switch x and y. And then we have to solve for y. So to do that, I'm going to subtract the 2 over. To undo a square, you're going to do a square root. But when you do the square root, you need to have the plus and minus on it. So square root with a plus and minus, x minus 2 equals y. And then my final answer, because I need to name it f inverse, is plus or minus square root of x minus 2. Then the last one, this is called y. So I'm going to get x equals, parentheses, y minus 2 cubed. I can't get to the y. To undo a cubed, you cubed root it. So cubed root of x equals, when you cubed root both sides, the cubed root and the cube undo each other. And then you add the 2 over. And then to write my final answer, f inverse of x equals the cubed root of x, and then plus 2. Okay, same process on this next one, only this next one's got a couple of steps. So, to find the inverse here, write the y down, and you're going to switch them. So you're going to get x equals 2y plus 3 over y minus 4. So I need to get all the y's on one side so I can solve for the y's. So to get rid of this fraction, I'm going to multiply both sides by y minus 4. And if I do it on one side, I'm going to do it on the other. These are going to cancel off. So now I have x times the y minus 4 that I multiplied over equals 2y plus 3. I'm going to distribute in the x. So I get xy minus 4x equals 2y plus 3. If I want to solve for y, I need to put all the things that have y on the same side. So I'm going to subtract the xy over. So now I have negative 4x equals 2y plus 3 minus xy. I'm going to subtract the 3 over the other side because it doesn't belong where it is. It doesn't have a y on it, and that is my y side. right now. So now I have negative 4x minus 3 equals 2y and a minus xy. All of my y's are on the same side. These both have a y, so I can factor out a y, and I'm left with 2 minus x. And on the other side, I still have my 4x minus 3. If I want to get this y by itself, I just need to divide. I need to divide by the 2 minus x. Oops, I forgot the minus. So my final answer is f inverse of x equals negative 4x minus 3 over 2 minus x. And then we should probably write x cannot equal 4. That was originally in that thing. The next example is a little bit less of an example. The book kind of does the problem for you. The blue is the original. So here's my original graph right here. And they tell me I have these dots. So 3, 1 is a dot. So if 3, 1 is a dot on the original, then on the inverse, you just flip them. So it becomes 1, 3. This dot right here, 1, 3. And on my original, if I have negative 4, 0, then on my inverse, I just flip them. I have 0, negative 4. So here's this, F, my original graph. It says I have 1, 1. When you flip 1, 1, it stays the same dot. But if I have 2, 4 on my inverse, it becomes 4, 2. And then you can graph your inverse like that. So let's make up one just for funsies. Let's say I said that f of x equals x squared minus 4. So x squared minus 4 is a parabola that went down 4. So there's a dot. That dot is 0, negative 4. And then if I plug in 1, I get negative 3. If I plug in 2, I get 0. So let's graph my inverse. So this dot was 1, negative 3, 2, 0, negative 2, 0, and negative 1, negative 3. So I want to graph my inverse. I'm going to start with 0, 4. 0, 4 becomes, 0, negative 4. 0, negative 4 becomes negative 4, 0. Right here. Negative 2, 0 becomes 0, negative 2. 2, 0 becomes 0, 2. Negative 1, negative 3 becomes negative 3, negative 1. And 1, negative 3 becomes negative 3, or positive 1. And then there's my inverse. Should have graphed. There's the original as well. Which is the same thing as reflecting across the line. Y equals x, because the y's become the x's and the x's become the y's. Okay, last problem. It says that I want to find the inverse with a restricted domain. So rules don't change, same procedure. Call this y. X equals the square root of y plus 5. And then we square both sides. So x squared equals y plus 5. And then we're going to subtract the 5 over. X squared minus 5 equals y, which we're going to write as f negative 1, or f inverse of x equals x squared minus 5. Now there's one little trick. This right here, because on the original, x had to be greater than or equal to 5, on the inverse, that means that the range is only going to be from negative 5 to infinity. But since x starts at x starts at 5, when I plug Sorry, this should be a -5. Oops. -5. So when I plug in a -5, let's see what happens with the range. So if this happens on my original, then my range of f of x is, when I plug a -5 in there, I get the square root of 0, so the range is 0 to infinity. Well, that range is going to go down here and be the restricted domain of this one, which means this thing's domain is greater than or equal to 0.